All right, so welcome back, everyone. I hope you are doing well, and we will continue our discussion on our motivic spaces and motivic spectra. We'll get there, but first, we are developing all our tools in our arsenal. In the last two lectures, we introduced simplicial sets. We saw some properties of simplicial sets, and in the first talk, I kind of foreshadowed something saying that doing homotopy theory on topological spaces or on simplicial sets are basically the same thing. Now, what do I mean by that? This is what I mean by that in today's talk. So for topological spaces, we defining we de we de defined our homotopy groups right here. Here the homotopy groups for topological spaces. You can see everything on the screen, right? As I'm writing down. Good.
Yeah.
Okay. So we defined using the homotopy classes of the maps between from sphere to the topological space. Now, a big feature of the topological spaces is that all the objects are fibrant. We don't say this, but this is the signature feature that we use to define homotopy groups and study their homotopy properties. This feature. What does that mean? We'll see that. Analogously, we have developed our simplicial sets. Here the problem is not all the objects are fibrant, but all the objects are cofibrant. Are not fibrant. Since being fibrant is a signature feature of defining homotopy groups, that means that it is a problem here. We can do something called as what this is what Khan did. This is what I think I explained, not explained, just mentioned in the first talk. And this is what Khan did. He introduced something called as EX infinity functor. That's your infinite subdivision of a simplicial set. And apparently that makes a simplicial set fibrant. And we can define the homotopy groups using this EX infinity functor. This is exactly what Khan did. This is his work from 1950s or so. And then he declared that, oh, if I compute homotopy groups of these simplicial sets, it's same as computing the homotopy groups of topological spaces. So doing homotopy theory in either of them is basically the same. This is your geometric. All the construction here are geometric. Here, all the construction will be your combinatorial. Now, what do I mean by their homotopy theory being same? That is for that in a refined theory of all homotopy features on arbitrary category. This is what Quillen introduced for studying this. This is what Quillen introduced in I think 1967 or so. And he called these features, he distilled all these features of these topological spaces and simplicial sets and declared a category called model category. What is that? They essentially model your homotopy theory. So what do I mean by that? Your model category will start with a category M, and it has three special type of morphisms. This is called cofibration. Fibration and weak equivalence. Let me write down fibration here. And this is your weak equivalence. Doing homotopy theory means that we are essentially playing with these morphisms in one way or the other and look at their properties. And we can look at their properties. We will look at their properties, in fact, but for now, let's just focus on how they interact with each other. What are the axioms? And these are the axioms. Your first axiom is that the category M is complete and co-complete. That means that it has all small limits and colimits. Okay. Your second feature is something called for the weak equivalences for 2 out of 3. 2 out of 3 property for weak equivalences. Now, what does that mean? If I have composition of morphisms like this, so what do we see in homotopy equivalence or in isomorphism? If any two of them, for homotopy equivalence, if any two of them are homotopy equivalent, then the third one will also be a homotopy equivalence, right? This is what we see in actual homotopy theory. And in fact, you can relax this for topological spaces. You can conclude something more. That is, if these were to be your normal weak equivalences, then the third one will also be weak equivalence. Now, for arbitrary model categories, we want this feature to be present, and that's why you take a part of this axiom. If any two of these weak equivalences that we have declared the arrows to be weak equivalences are part of, are weak equivalences, then the third one is so. The third axiom is your factorization axiom. For that, let me motivate you first. So yeah, for topological spaces, what do we see? So if I have a map between topological spaces in top, if I have a map between topological spaces, I can always factor through this map to its mapping cylinder, right? Such that your B is homotopy equivalent to your MF. And this guy turns out to be an inclusion, a special inclusion. These are called cofibration in topological spaces. Also, it can be also be factored through as path spaces. PF, such that this line is your cofibration and this is your homotopy equivalence. Yeah, the slogan is all the maps in topological spaces are basically cofibrations or composition of cofibration and fibrations. That's all. So we want a feature like that for doing homotopy theory in arbitrary categories. And that's what it's called factorization axiom. This tells you, yeah. So this is your motivation. What this tells you that any map A to B in your model category will factor through a cofibration followed by a trivial fibration, and by the way, a map that is weak equivalence and a fibration are called trivial fibration. A map that is your um, weak equivalence and a cofibration are called trivial cofibrations. Okay, and it can be factored through, let's call this object D, a trivial cofibration followed by a fibration. We can factor any map like this in our model structure, in our model category. All right, so far so good. Halfway there, and
So I have a quick question.
yeah.
So we defined, mapping cylinders and last time we didn't find the path space, but like what is that supposed to mean in an arbitrary model category? Is this some data that we're adding to, or should this be constructed from limits and colimits?
Yeah, yeah. The thing is that you can define path space in arbitrary model category as well in terms of some limits that I have kind of forgotten. These are called cylinder object and path object. I have to take a look on them, but that is not really important while we are doing the factorization. So if that makes sense.
Oh, okay. So right now we're just saying it has some factorization of this form. Um,
Yeah, this is
are
just your motivation to tell you that we want this factorization in our axiom. That's all.
okay,
Like
okay. So we're assuming it.
we
Uh,
are not saying that it splits through your cylinder
are
object or path object yet.
are we assuming any uniqueness in terms of like what? I mean,
No,
a priori.
we are
Okay, no.
assuming
Okay,
that this factor, yeah, but yeah, let me say this here. We are assuming this factorization is functorial. That means that if I use another factorization like this, I have a natural morphism like coming from one object to the other. So in a commutative diagram, your factorization will not affect the diagram itself. That's what you're assuming.
okay.
Yeah. Yeah. So this factorization, no, no, yeah, this is a good question. So we can not only factor these factorizations are functorial, meaning that in a commutative diagram, doesn't matter the way you factor. That's all. That's all it means. Cool. And yeah, um, yeah. Then let's move on to the next property that we need. That is your lifting property.
So,
So
so maybe we could
yeah.
uh, pause on that a moment. So I think that the definition I've typically seen does not require it to be functorial. And even if you want it to be functorial, you have to be a little careful because these factorizations are usually not unique. So you could
Hmm.
require that it's possible to make it functorial, but it still isn't true that every factorization arises from the functor. Like this is uh
Um,
Yeah, so I feel like the functionality should be something like the factorization plus lifting or something. Um,
but
like the
I think like Quillen's definition did not have functoriality.
yeah,
But
Quillen's
that
definition did not have functoriality, but the thing is that yeah, we need kind of functoriality in Kane-Brown's lemma, and you know, uh, now I'm a little bit confused. Should I add this in your axiom or not? Maybe if we remove this, will we still be fine? But then we have to refine the lemma, saying that okay, there exists a functorial factorization there. So I
but
guess
okay, well yeah, we can see when we get to
yeah, I guess up to you. Like if you want to take it or not. That's all. Let's just say the factorization exists for now. Then cool. Okay. Um, the lifting properties are kind of matches with your lifting properties in your in your topological spaces that your co-fibrations. I won't say this, but yeah, no, not really matches with topological spaces. But at least we know this for the Serif fibrations. You get the lifting with respect to your CW complexes, right? And we want something like that for in our model category. That tells you, so what is that axiom? So if you have a trivial fibration here and co-fibration here, then there exists a lift. Um, if I have a trivial co-fibration here and a normal fibration on the right hand side, then we have a lift. Yep, that's the axiom. That tells you that trivial cofibration and fibration has less lifting property with respect to your fibrations and trivial fibrations. All right. Yeah. The next axiom is your retract axiom. So retract of a homotopy equivalence is again a homotopy equivalence. So this is called a retract diagram. So um, call this map B to B prime G and call this map A to A prime F. And this is also your F. So F is called retract of G. If this diagram is satisfied. And what you want is that our weak equivalences, cofibration, and fibrations, they're all being preserved under read traps. So if G belongs to any of these classes, cofibration, fibration W, so does F. Okay. And the last, this is not an axiom, you can take it a part of your definition or not. In the notes they have, that is, your model category comes with a initial and terminal object. Initial, call this initial, and I don't know, terminal object 1, I guess. Yeah. So these are all your axioms. Any questions so far for the axioms itself, other than your functorial factorization?
So for the lifting, is that unique or just need one lifting?
There exists a lift. Yeah, it doesn't have to be unique. Yeah.
Okay.
Anything else?
Why is there initial and terminal? Is this just like I mean they're completing co-complete, so like is this are we adding some smallness condition on M? Like if the
Yeah,
objects
so
form a set or
yeah,
something?
we just want to talk about cofibrant and fibrant objects all the time. That's why we take them. Otherwise, how else would you talk about fibrant and cofibrant objects, right?
I think Colton's point is that they already exist because you already assume that M has small limits and colimits.
Oh,
Yeah,
I
like
see. I see.
yeah, I don't think this is an assumption. I think this is
Okay,
all.
so small limits and colimits means that it has initial and terminal objects, right?
Like if your category is locally small, uh, or maybe slightly stronger than locally small, so something like this, then yes.
Can you say how? Like, how does it happen? Like, then I'll be clear.
Well, I mean, like, uh, you can write some, if you have sufficiently small a number of objects, then you can write a diagram whose limit is the initial object and likewise the co-limit. So I think you just need that like you need some set of objects who have a morphism to every object.
Why do you need any local smallness? Isn't the initial object is the co-limit of the empty diagram and the final object is the limit of the empty diagram. Isn't it just that?
Ah,
I
no,
see.
yeah, I think you're right. Yeah.
Okay, you can defining that as a. Okay, I see. Okay, as a co-limit and limit of empty diagrams. I see. Okay, then we don't need it. Thank you. Thank you so much, Pramod. So the point is that a corollary, it comes with initial and terminal. Thank you for clarifying this. All right. So yeah, a big feature of talking about model categories is that we said that we need three class of morphisms, but we actually don't need three. We can determine the other class by knowing just two. For that, these are the lemmas. Let's look at them. So yeah. So this is your first lemma. This one. So if I map like F factors through Z with a left component is L, right component is R compose L, then if F has your left lifting property, left lifting property with respect to R, then F is a retract of L. Yeah, let me write let me underline this. F is a retract of L. Now, how does this happen? Let's look at it. So you're saying that F has a left lifting property with respect to R. So first of all, from this diagram here, we can reach this diagram over here. Okay, it's easy to see. And I can lift this map over here to Y to Z by the axiom, by the assumption. Now, again, from this diagram over here, I can reach this diagram over here, the retract diagram. And this will be a retract diagram if this lift exists, which it does by this axiom. So now this R compose, this blue arrow is your identity on Y. That's what you get here, identity on Y. This identity is your this identity over here, and that is your on your top row. Everything is identical. You don't have to worry about that. So this is a retract diagram. So F is retract of L. That means that whatever L is, cofibration, vibration, or weak equivalence, so will be your F. Okay, by your retract axiom of your model category. Now from here, you can conclude this. A map F either is a cofibration or a trivial cofibration if and only if F has left lifting property with respect to the maps in either in, so for cofibration, trivial fibration, and for trivial cofibration, lifting property with respect to fibration. Now a map is a fibration or a trivial fibration if and only if it has a right lifting property, analogous version of that with respect to the maps in cofibration, trivial cofibration or cofibration. That means any two of cofibration, fibration, or weak equivalence will determine the third. This is the signature feature of model category. This is your signature feature. That means I can get away by giving you just two classes of morphism and say that, oh, determine the other by using your lifting properties. Cool. Yeah. So in your normal topological spaces, your cofibrations and your cofibrations are closed under push out, coproduct, and your sequential colimits, right? Same is true for these push outs over here. Same is true for these cofibrations over here. They are closed under push out of a cofibration or a trivial cofibration is again a cofibration. Or trivial cofibration respectively. Yeah, how? Let's see it. So this is your diagram of a cofibration. Let's give this diagram object names. So this is your A, this is your B, this is your C, this is your D. Okay, call this P, call this Q. So D is your push out of this diagram. A to C is your cofibration. Now I want to show this B to D is a cofibration. That's what it means, right? Push out of a cofibration is cofibration. That means that it is a cofibration if and only if now we use this first feature in this line. That I need lifting. I need the lifting here. How do I get the lift here? For that, I use the fact, okay, this is a trivial cofibration. So for that, I use the fact that we have a lift here from C to P. And Okay, I'm tripping a little bit. Hmm. So how do we get the map out? It shouldn't be this hard. I'm tripping.
Use the definition of push out.
Oh yeah, I didn't use the definition of push out yet. Right. So we have the map from C to P and B to P. That means that we get this map by the universal property of push out. Thank you so much for chiming in. Yeah, there you go. Yeah, and dually you can prove taking the dual diagram. It is the pullback of a vibration is a vibration. Pullback of a So again, you can show this by using lifting properties. And this is also closed under sequential co-limits and limits. Co-fibrations. So this is for co-fibrations. This is for vibrations. So this is how your co-fibration vibrations, they quite nicely interact with each other.
May I ask a question?
Yeah,
Go back one slide.
yeah.
So you say any two of C, F, and W determine the third.
Yeah.
How does C and F determine W?
Yeah, so from C and F, you will determine C intersection W from F, and you will determine F intersection W, right? Now you use this feature. Let's write this down here. So this is your weak I mean, yeah. Now a weak equivalence, if it is a weak equivalence, it has to factor through this, right? Like this. So you can take composition, now you can forget this. Now you can take composition of weak trivial cofibration and trivial fibrations. All of their composition will give you the weak equivalence. Does that answer your question?
Yeah, I think so. Thank you.
Okay. Okay. Let's move on to the next topic. Now, to study the homotopical feature, homotopy groups, or homotopy equivalence, we need to define something called as cofibrant and fibrant objects. That's what I mentioned in the beginning of the talk. So let's talk about them. Your cofibrant object is an object X if from the initial object, this unique morphism is a cofibration. This is your condition over here. And it's a fibrant object if your unique map to your terminal object is a fibration. Cool. Now, yeah, this is a question like, when does the functor between two model categories preserve your weak equivalences? This is the question we are going to answer. And for that, we need to introduce something called as Kane-Brown's lemma. And it's a very cute lemma, meaning that you'll see all the features of your model categories taking a part in this proof. Yep. So let's look at them. So yeah, so what is the lemma? So a map between two cofibrant objects, your A and B, both are cofibrant. Then there exists an object CF, and there exists an map JF from B to C, such that this is your trivial cofibration. First of all, this map is your trivial cofibration, such that it fits into this diagram. Um, boom. Making this diagram commute. Yeah, is the proposition clear? Then I will come to the proof. Is the proposition clear here? Yeah, so here not only the CF and GF exist, they exist functorially. That means that if you this CF, you can replace this CF by CF prime, and then you'll have another GF prime making the diagram commute. So this is what I mean by functorial factorization, and this is what I wanted to like emphasize on in the beginning. Does it give some validation or something?
I think I'm still confused a little bit about
Okay.
in what sense is functorial. So like CF or MF or these constructions,
Yep.
they're not literally like they're not literally unique. They should be like unique up to weak equivalents, right?
Yeah. Yeah, let me actually draw a diagram for you. Maybe that will help you to see what I mean by functorial factorization. So this is maybe what I understand and what you understand, they are different. So let me use a different page for functorial factorization. So let's take commutative diagram X, C, Y, W over here. So this is your U, this is your F, this is your G, and this is your Y. Now, yeah, if you break this diagram down in terms of your L and R, I mean your left and right classes. So X2, boom. Yeah, let's use, doesn't matter. Let's use E here. Boom. C, E prime. This is your W. Boom. Damn. Then there exists an arrow between E to E prime, making the diagram commute. So the way I understand functorial factorization is that your commutative diagrams are not affected by your choice of factorization. That's all. That's all I understand. If there is other notion, then let me know.
Well, and the middle arrow should be a weak equivalence. Or no, sorry.
No, the middle arrow
if
exists.
if
It exists and make the diagram commutes. Yeah.
if you take Z and W to be X and Y and G to be F, then it should be a weak equivalence. Right?
Okay.
Right, I mean, there should be some sort of like
You're saying
some
this. Okay.
version of uniqueness for these things. I mean, it's not like
I think the
I
confusion here is you're not asserting that the arrow from E to E prime is unique, only that it exists.
yes, that's
There may,
fine.
I mean, if you think of exact sequences, you can have you think of it a chain, just exact sequences. You can have a map of exact sequences for which you have an arrow on the, the kernel and the co-kernel, but there are many arrows in between. It's not, so when you assert the existence of a map from E to E prime, you're not claiming it's unique, I don't think. Now that's a very strong axiom, which I think is too strong, actually.
Yeah, no, I wasn't suggesting that. I mean, it follows from just composition that the E to E prime is a weak equivalence. So,
Oh,
right, it's both
well,
fibrant and cofibrant.
Yeah.
That's all I was saying. Right,
Okay.
I mean, there should be some sense in like these objects are unique up to a non-unique weak equivalence, right? Anyway, I'm satisfied. Thanks.
Yeah, Professor Acha, you wanted to say something, or did you?
I mean, maybe this will be clear after we do the proof, but yeah, I mean, is the existence of that horizontal error something extra to impose, or is it just going to be like, isn't it going to be a consequence of one of those lifting properties?
Okay, that's a good question. I think in the notes that I have, yeah, that I can see, to tell you right now, in Real's node, they assume the functorial factorizations and they take them into account by default. But existence of that might be proved from the lifting properties. Okay, yeah, I have to clear that out then. I will clear that out. Clear out the necessity of, yeah, this is my task, necessity of functorial factorizations in the definition. Okay. Let's just forget all that and let's just see the proof of the Kane-Brown's lemma. Oh, where is that? Yeah, Kane-Brown's lemma. So, yeah. So, what you are trying to construct is a map from B to CF, such that, okay, let's take this down a little bit, such that this diagram commutes. This entire diagram commutes. This is what we are trying to show. Now, for that, so we know that A and B are both cofibrant. That means that we get to use, these are your cofibrations. A push out of your cofibration is a cofibration. That means that the push out, on the push out side, they will induce a cofibration, right? Cool. Now, good. Let me. Now, this is a push out diagram. That means that if I look at this map, P here, this is your identity on B, and A to B, the map is your F, this F. It goes in here. That will induce your natural map. I don't know, F IDB, your universal map, out of your push out. This map can be factored into this guy, this CF. So this A disjoint union B, this guy is your F disjoint union IDB. I did not write this down, but let's see. Do I have the, yeah, I have this. Write this down here. And your A, this is a cofibration map. A to B, we have the map, your F, and from here, B to B, we have the map, your identity B. Yeah, taking the composition. Okay, this is also a cofibration. Taking composition of this arrow and this arrow, we will get this arrow. I didn't say this, but yeah, we can also say that compositions of cofibrations is again a cofibration. So now we have to chase the diagram. So this is your IDB, this is your weak equivalence. This guy has, this is CF to B is your weak equivalence. That means by 2 out of 3 property, this guy is a weak equivalence, B to CF, right? Yep. So this is your the required JF map that we are looking for. And that, yeah, that completes the proof. Does it complete the proof or I'm missing something?
Why do you have a map from push out to CF?
Why do I have a map from push out to CF? This is by the factorization axiom of of any maps. They can be factored by a cofibration and a trivial fibration, right? So this A disjoint union B to B, sorry, coproduct of B to B. This map can be factored through some object that I'm calling that object CF. Yeah, now I'm trying to think how can I use this functorial factorization into the picture. So,
Well, so I think the
yeah,
functorial part is that you have a map, or you have
mhm,
factorization now from A to CF to B,
yeah.
and by the functorality, CF is actually weak equivalent to what you wrote CF before, right? So it
The thing is
actually
that
is.
it doesn't
Yep.
have to be weak equivalent. It can be an arrow from this previous CF to yeah. So something like this. So A to B, this map can be factored like CF prime to B like
But it
that.
is weak equivalent,
How do you know
right?
it's weak equivalent? Oh yeah, it
Because
is weak equivalent.
they're two.
Yeah.
Yeah.
Yep. This is weak equivalent. Yes. So in this case, this is weak equivalent, and in this case, as you are saying, it justifies the cause. But yeah, the existence of the arrow is good enough for the weak equivalence case. That's what I understand. But yeah, in this case, it's easy to see. So yep. Anyway, um, and dually, yeah, let me write this dual picture here. Dually, if I have a map and this guy is your trivial cofib, if you factor them like this, then there exists an object PF and a map from PF to A to PF, which is a trivial fibration, making the diagram commute. So these are the dual version of Kane-Brown's lemma, proved in similar way. Yeah, questions here now. Yeah, let's see. So we used all the features of model categories in this one proof. That's why I like this proof a lot. The only feature you did not use is the retract. Okay, but other than that, we used everything. All right, let's move on then. Yeah, a corollary of this Kane-Brown lemma will give you the question that we asked for. So a functor between model categories, so M and N are your model categories. These preserve your trivial cofibrations. Then it sends your weak equivalence between cofibrant objects to weak equivalences. Yeah. How? So it sends your trivial cofibrations to your trivial cofibrations, right? Now, to see that it preserves your weak equivalence, we will use the Kane-Brown's lemma. So what do we have here? We have A to B weak equivalence. I want to show FA to FB is a weak equivalence. Now, by Kane-Brown's lemma, I have this diagram. Boom, boom, CF to B is a factorization. This is your weak equivalence. Now, by 2 out of 3 property, this will force this cofibration to be your weak equivalence. And I'm applying Kane-Brown's lemma to get this map, making the diagram commute. So if I apply the functor here over here, then I will get this guy CF then F of B, F of CF, F of B. This is your equality, and this is your fibration. Now what do we have? We do not know if it takes a trivial fibration to fibrations, but we know at least these two will be preserved, trivial cofibrations. Now, this is a commutative diagram, and that means that, okay, equality means this is a trivial weak equivalence, and that means that this guy is a weak equivalence, and that will mean that by 2 out of 3 property, this guy is a weak equivalence. So it takes weak equivalences to weak equivalences. Are you good? Okay, let's move on. Yeah, if I don't hear any answer to if you're good or not, I will assume that we are good. Okay. So the next thing is talking about homotopy categories given a model category. There are 3 ways of doing that. So let's see all the ways. So given given A cofibrant, and B fibrant, so given between cofibrant and fibrant objects, we can define something called as left and right homotopy equivalences. And so for any object, okay, between any 2 objects in the model category, we can define something called as left homotopy and right homotopy. The thing is that if your A is your cofibrant and B is your fibrant, then these 2 homotopy coincide, giving you the notion of homotopy equivalence. A, B, left. So 2 maps between a cofibrant to a fibrant object are called equivalent if they are either left or right equivalent. I'm not defining them. Just say that they have a notion, because I have to define a lot of things. We have to define cylinder object, we have to define the path object, and we have to talk a lot about them. So I'm not when you do that, they have a notion of homotopy. Given the notion of homotopy, the standard way to give you the homotopy class or homotopy category is to that quotient out by this relation and see what they are. Now the problem is not all the objects have to be cofibrant, but not all the objects have to be fibrant, and that's where you use another feature of model categories, that any object can be replaced by a cofibrant and the fibrant replace an object um, up to an weak equivalence. So we define this as a morphism between this guy modulo your homotopy equivalence. So what is this QA thingy? So your QA to A, this is your weak equivalence such that this guy is a cofibration. This guy, I mean, QA is your cofibrant object, and your RA. So this is your for QA, and for RA, it is given A. You can replace by something called as fibrant replacement, that such that this guy, this unique map, is a fibration. Yeah, we can do this for model categories. So the fact that to state that this Q and R are functor, you also need your functorial factorization. So what you're doing here is that you're factoring this map, this unique map, through this guy, and through this through this guy. Yep. Now to state that Q and R are your natural transformation from Q to IDM, we need the fact that it's a functorial factorization. Otherwise, we can't conclude. Do you guys see this? Or am I the only one tripping? Anyway, if I'm tripping, doesn't matter. You can replace this up to weak equivalence. You can replace this A by QA and by RA such that your QA is your cofibrant object and this is your RA is your fibrant object. So you can replace this, bifibrantly and take the homotopy classes in this notion. You will get something called as HOM. And another big feature of your this model category is that your weak equivalence between bifibrant objects actually is your homotopy equivalence. That's another something that I'm again sweeping under the rug. So that way you can also define your HMCF. So what is that? That is your here objects are your bifibrant objects. That is your cofibrant and fibrant. And yeah, and your morphisms between them are basically looking at the morphisms between in the model category modulo your the homotopy equivalence relation. Now saying this as same as saying by the theorem that I just mentioned, we can look them up to weak equivalences as well. Yeah, and the third way of the third category that we can define is by inverting your weak equivalences by this localization functor. So this means that we are looking at all the zigzags. So boom, 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 boom. This thing is this thing. This is a weak equivalence. So this thing is your one arrow in this category. So you're formally inverting all the weak equivalences. There's a classification property with like localization functor, just like you use your localization with respect to your, in the set of rings. But I'm not going to write that down. The point that I'm trying to make here is that all these three constructions are equivalent. So it's actually easy to see these two are equivalent. And Quillen showed these two are equivalent. So that means that all three are equivalent. So yeah, the popular notion of your homotopy category is this guy. So that means that I don't need to, so that means that I don't need to define your left and right homotopy classes or anything like that to actually talk about, the homotopy category. I will just look at the model category. That means that I have the weak equivalences. I would formally invert the weak equivalences and talk about the homotopy category. So that's the point I'm trying to make. Is it clear?
And these are equivalent as honest categories, not in any model theoretic sense.
Yeah, these are equivalent as your honest categories. Yes.
Okay.
Yeah. So we don't need the notion of homotopy to talk about homotopy. That's the thing we see. This is your homotopy category of M. Cool. Yeah. So far we have talked so much about the features. Now let's talk about a few examples. The first example should be your topological spaces, right? Here I mentioned, all the objects are your cofibrant. Oh, sorry, fibrant. This is a big feature of topological spaces. Now let's look at what all the maps are. What are your weak equivalences are? Your weak equivalences are your weak homotopy equivalences. And your fibrations are your shared fibration. What are they? That means that, so let's talk about homotopy lifting property first. This is your homotopy lifting property. If I have a homotopy here, x cross I to b, and such that I have a0 tilde here, that means that I can lift this entire homotopy over here. If this exists, we call that property homotopy lifting property. Now, what is a serif fibration? Serif fibration means that I have homotopy lifting property with respect to all CW complexes. That means I have respect to all CW complexes. Now, if you relax this a bit, what does that mean? With respect to all CW complexes, that means that I have by default, okay, I need some more space. Okay, it's a very bad space management, but okay, because this side is empty over here. Okay, so that means that for disks, yeah, for disks I have yeah. So since this enjoys your HLP with respect to all CW complexes, that for means that if I replace your X by your DN, your disk, it will enjoy your homotopy lifting property, right? Cool. Now it's a nice exercise that if I take your trivial self vibration, if I take trivial self vibration, E2B is your trivial self vibration, then I will have lifting with respect to this guy. Now, as you have already seen, cofibrations are all those map that has lifting with respect to your trivial fibrations, right? You remember that? This guy, delta dn to dn, enjoys left lifting property with respect to your trivial self vibration. What does that mean? That means that this guy, this delta, okay, let's write down here first. This delta dn to dn must be a cofibration. Do you agree with me so far? So cofibrations are the maps that enjoy lifting with respect to your fibration. That means that if I take at least this delta dn to dn, these maps they are cofibrations in this category. Do you agree with this? Okay, everyone agree with this. Now see this feature. Now, if I take push out with respect to all these guys, call this xi plus 1. Okay, I take the push out. That means that since this guy is a cofibration, their push out is also a cofibrations, right? What does that mean? I can keep taking these iterated push outs and I will still get a cofibrations. And it turns out these are all your possible cofibrations. So these are called I cells. No. I lied a little bit. These are all your cofibrations, and you can take your retract of these cofibrations. That again, it will be your cofibrations. So all your push outs of your this trivial not, I shouldn't call this trivial. This, this is called, I forgot what it's called. This is called generating set for, this is your generating set for cofibrations. So if I take this generating set and take its, all possible push outs, iterated push outs and all possible retracts, you get the set of cofibrations for topological space. This is a big feature of topological space. These are called I cells. Or I cell complex. It is called I cell complex if, or I cell map. I forgot what it's called. So what I mean by that is that this map X to Y can be obtained by this push out of this diagram or its retract. That's all it means. And that is your I cell. These are all cofibrations. And how do you determine all the trivial cofibrations? For that, so look at this guy. So E to B, this is your E to B. Okay, that's so small now. E to B, this is your cofibration, right? So that means that this guy over here, it has to be trivial fibration. Now let's look at this guy, dn cross 0 to dn cross I. You can, this is your trivial cofibration, and same thing repeated again. These are called JSA complex, cell complex, so, or JSL maps, I forgot the name. But what you do is you take their iterative push outs and take their retracts to get all the trivial cofibrations. Yes? You have any question? Professor Wang, do you have anything to say?
Yeah, I'm fine.
You're fine? Oh, you turned in your voice. You leaned in. I thought what's going on. Are you guys fine with this? So this is a big feature of topological spaces. A model category for which you can take a generating sets and get the cofibrations like this are called cofibrantly generated categories, model categories. And most category that we have seen and we'll see are all cofibrantly generated. Okay. Yeah. So this is your topological spaces. So now let's look at the model structure on simplicial sets. So for simplicial sets, all your objects will be your cofibrant. We'll see how this is true. Yeah, oh, and by the way, why are all the objects fibrant? Because if you take any element here and map it to your terminal object in this topological spaces, that is your point. So you can take, basically you can lift over there, right? So this is your another CW complex, I don't know, Y cross 0, and this is your Y cross I. If I have a homotopy here, if I have a A0 tilde here, this exists, right? Yeah. And here all your objects are cofibrant. Your weak equivalences, there are two ways of defining this. One is you're using your EX infinity functor and doing your infinite subdivisions and define the homotopy groups on the fibrant objects. But forget that, we'll encounter that in the next class. What we'll see is this guy. We say that a map between two simplicial simplicial sets are weak equivalent if their geometry realizations are weak equivalent. That is your weak equivalence. Your fibrations are basically this guy. So x to y is a fibration. So del nk is your horn, kth horn. That is, you take out the from the boundary of the n cell, you take out the face opposite to the kth vertex. And yeah, these two are equivalent because their geometry realization is basically will be your a simplex and your horn. A horn is homotopy equivalent to your your simplex, right? Geometric simplex. So this is your weak equivalence over here, and yeah, I did not define what cofibrations are, but this will turn out to be your cofibration because all the cofibrations will be your inclusions. But anyway, so I will call this guy a fibration if I have this left for all n and k. These are called Kahn fibrations. And your cofibrations are monomorphisms or inclusions, K subset L. And it turns out any simplicial set L can be constructed. So given any morphism like this K, some subsimplicial set of L, I can construct this guy K, K0, K1. These are all simplicial sets. Then take the co-limit of all Ki's, and I will end up with L. Now, what is this K0 to K1? Guess what? This is what you get by attaching cells. This is your delta dn. This is your delta n. Boom. Sorry, not that. A push out as a push out. So is Ki to Ki plus 1. And yeah, that means that you can declare this delta dn to dn as your generating set for your cofibrations. This is your generating set for cofibrations.
To delta n, right? Not dn, to delta.
Yeah. Delta n. Sorry. You will literally declare them your generating set for your cofibrations, and you'll get all your cofibrations for back. So we don't need to look at all the maps. We can look at some sub collection of the maps, and we'll be done. These are also a big feature of your, in particular, these categories, and these are called. So for categories that enjoys a generating cofibrantly generating, maps, these are called cofibrantly generated model categories. So these two are called cofibrantly generated model cats. We'll see more examples with time with spectra, with chain complexes and abelian groups and all that. But for now, these two examples are sufficient. Now let's focus on the next notion of your model categories. That what Quillen did for us, your proper model category. But let me take a break before that. Any questions so far?
Sorry, I think I'll have to leave in a couple minutes, but
yeah. But you have a question, yeah.
No, I don't have a question. I was just letting you know that I'll leave at some point.
Okay. Never mind then. Okay. But yeah, let's end this. Like I have 1, 2, 3, 4 things to talk about. So I'm going to speed up, like storm through it. Let's see. Let's talk about proper model categories. So this topological category of simplicial set, category of simplicial abelian groups, these are all proper. What do I mean by proper is that, okay, let's talk about left proper. So this is called left proper. If I start with this push out diagram, this is your push out diagram with the condition that this is your cofibration. That means because this is a push out diagram, you by default you have a cofibration over here. And if this guy A to B is a weak equivalence, then we will end up with a weak equivalence over here. This is what it means by being a left proper. Your C2D map is a weak equivalence. This is called right proper. If for a pullback diagram like this, now if this is your weak equivalence C2D, your A to B will be your weak equivalence. So we didn't have any conditions on the or any property of the weak equivalence in terms of your push out and pullbacks. Now we do. So weak equivalences also respect the push out and pullback diagrams. So it is called left and it is called both left and right proper. If it is both left and right proper, then it is called proper. And guess what? Most model categories that we'll encounter and see are proper. Simplicial sets, pointed simplicial sets, topological spaces, pointed topological
Right.
spaces,
For
spectra.
right proper, do we need to assume the vertical maps
Oh
are
yeah. Sorry. Yeah. This map is a vibration. Yep. Thank you. And this by default will be a vibration. Yeah. We do need to assume that. Thank you. All right, that's your proper model category. Yeah. Okay. Let's see how much we can talk about. Let's not talk about projective structure for now. Let's talk about your Quillen equivalence because I think that will be a good place to. I think we can stop today's talk. Yeah. So this is this projective structure and your this simplicial model categories. These are some uh, extra features that Quillen did in his I think in his paper on the simplicial model categories, I guess. But we'll see that later. But for now, let's focus on Quillen functors. So we want a functor between two model categories, preserving the model structure, right? That's what we want. Uh, that's why we want a functor to behave like. So I will call a left Quillen functor f such that m to n if f has a right adjoint and f preserves your cofibrations and trivial cofibrations. Yeah, f enjoys an adjoint and it will preserve your left adjoint will preserve your cofibrations and trivial cofibrations, and equivalently g the right adjoint g, so g is your right adjoint. F has a right adjoint, call it g. G preserves your fibrations and trivial fibrations. How? Let's look at it how. So yeah, what does the adjunction mean? So a map between fa to x correspond to a map between a to gx, right? So what do you want to show? If I start with a fibration over here, apply ga to gb, I want to get this map to be a fibration. For that, I use the lifting property. This is how you determine the fibration. Check if it has lifting property with respect to your trivial cofibration. So choose x to y, your trivial cofibration. Boom, boom, boom. Such that this diagram commutes. Now this diagram will give me an analogous diagram by the adjunction here. Fx to a to b to fy b. Boom. Now f preserves your trivial cofibration, so that means that this will be preserved, and yeah, that means that this will be preserved. And I started with the assumption that a to b is a fibration, so that means that this guy is a fibration, meaning that this lift exists, and that means that this lift exists by the adjunction property. Cool. Good. Now, so a left Quillen functor is basically left adjoint and equivalent if G preserves your, so this is your right Quillen functor, equivalently you can define. Equivalently define right Quillen functor like this. Cool. And it is called a Quillen equivalence if for all A belongs a cofibrant object of M and B your all fibrant object in N, this equivalence of adjunction, right? This is your adjunction equivalence Fa to X, yes, will restrict to the weak classes. So I will explain what is actually is doing. This means that it is essentially preserving your homotopy structure based on the discussion we just had a few minutes back. So A is your cofibrant, X is your fibrant. That means that your GX is your fibrant, right? A to GX, your left and right homotopy coincide. So that means that it has a notion of homotopy equivalence, right? And okay, okay, it may not be very obvious from here, but or what I'm trying to say is that if A also enjoys your fibrant structure and GX also enjoy your cofibrant structure, then your weak equivalences between them is your essentially your homotopy classes, and this on the right side you also get homotopy classes and their structure being preserved. But that creates some extra condition. It's a little bit relaxed condition than that. Yeah, go ahead, Professor Hoffman. Go ahead.
Yeah. Do you really mean to write M of A GX or M of A GB?
I need. Yeah, so I'm looking at the a cofibrant object of M and B a fibrant object of N. This is what I,
Yes.
yeah.
Yeah, you're saying there's a typo. X should be B to make it make sense with what you wrote. Or B should be X.
Where is the type? Oh, okay. Okay. Yeah. Right.
Thank you.
Yes.
Sorry, and the interpretation we should have with Quillen equivalents is that these are not actual equivalences of categories in any sense, but they should be the ones that induce equivalences when we pass the homotopy categories. Correct?
Yes. This is how you should think of them. So if this A was your bifibrant object and this X was your bifibrant object, this will give your actual homotopy classes, right? So does your A and X over there. So they induce your homotopy classes. So if that does that help? Like,
I think your question is, does it induce an equivalence of homotopy categories? And the answer is yes.
yeah, the answer is yes, and you can see it from there. That's what I'm trying to say.
Yeah,
Yeah.
no, I can see it. It was more of a comment than a question.
Yes. So this will tell you that your homotopy categories here, M, W, M inverse is equivalent to your M up, N weak, N inverse. Yeah, for that we have to go to your HMCF and show them these are equivalent. HNCF. Yep. From here, you go here. Okay. We'll see examples. Okay, but I want to make a remark first. Okay, let's see the example. Then I will make the remark and we'll end this. So your simplicial set to topological spaces, this geometry realization is a left Quillen functor, and it induces your Quillen equivalence. This is your Quillen equivalence. Your simplicial sets to your pointed simplicial set, that's also a left Quillen. Not a Quillen equivalence, I don't think so, but it's a Quillen functor for sure. And then your simplicial
Sorry, to
sets.
pointed. Oh,
Yeah, pointed here to the free abelian group operator landing on abelian groups. This also induce, this is a free functor, this also induce a Quillen. These are your Quillen functor. Let's end this with a remark, and then I will take questions. If both F and G, so the left Quillen functor and its right adjunction, the right Quillen functor, they preserve, weak equivalences, then F is a Quillen equivalence. If and only if for all bifibrant objects, A belongs to M and B belongs X, not B. X belongs to N, we have the following weak equivalences. The unit and co-unit, they will induce weak equivalence. Unit and co-unit of that junction. So this is your co-unit and unit. Yeah, how is this true? So for that, to see this, how is this true? So yeah, start with your bifibrant objects. Yeah, start with that F is a Quillen equivalence. Start with the fact that it is a Quillen equivalence. Then yeah, let's say that F is your Quillen equivalence. Then so is G, right? Then so is G. I want to show that for all bifibrant objects, A belongs to M and X belongs to N, this guy is a weak equivalence, A to GFA. So A to GX over here, and GX, yep, A to GX, and let's apply F here. F of A to F of G of X. Now F of G of X to X, I have the map, the unit map, right? F of G of X to X. That will induce a map from F of A, applying F here, F of X. Okay. Yeah. Now if F of A to X is so A is your bifibrant object. In particular, that means that F of A is your cofibrant, F of A is also your cofibrant, X is your fibrant, then means that it's if it is a weak equivalence here, yeah. So if it is a weak equivalence over here, then okay. if f of a to x is a weak equivalence, then means that a to gx is a weak equivalence by your Quillen equivalence. Applying f preserves your weak equivalences. That means that you get this f of a to f of gx by the axiom. Now, by 2 out of 3 property, this will give you your weak equivalence. Oh gosh. Okay. And similarly, okay, yeah, and I can see that I can see it now. So similarly, you start with your f of a to x, apply the g. This is your gf a to gx. This is your g of a to g of gf a to gx, and this is your a to g of a to gx. It is the adjoint map to f of a to x. Now, by Quillen equivalence condition, if your a to gx map is your weak equivalence over here, then a to g of, yeah, then this map is your weak equivalence, this map is your weak equivalence, and this is your weak equivalence. And this is an if and only if condition, the 2 out of 3 property. If your a to g of a, this guy is a weak equivalence, then you can, yeah, you can literally, I think, trace back, and it should not be that hard. I will stop here for now. Okay. And we can talk about it. All right, let me stop the recording.